Good morning from Scotland. Virtually welcome to Glasgow, which we believe to be home to the world's only Eulerian subway system. Though if anyone listening knows a counterexample, please do let me know so I stop saying this. And we're very happy to be virtually hosting Heng Guo from the University of Edinburgh. He's done all kinds of exciting things in counting and sampling complexity, recently been awarded an ERC grant in this topic. And today he's going to tell us about a Markov chain approach towards the sampling Lovász local lemma. So over to you, Heng.
Thanks. Yeah, it's a great pleasure to participate in the Round World Relay in Combinatorics event. Yeah, thanks a lot for inviting me. So today I'm going to talk about this Markov chain approach towards the sampling local lemma. So basically, it's some algorithmic questions related to the local lemma. And this is a joint work with Wei Mingfeng, Yi Tongyin from Nanjing University and Chihao Zhang from Shanghai Jiao Tong University. Okay, so let me try to first define the problem. So for that, I will introduce the Lovász local lemma. Of course, this is the classic result in combinatorics. I'm sure many of you are familiar. So basically, you want to find some kind of combinatorial structure, let's say, and the kind of standard probabilistic method would be you try to come up with some probability space so that the probability of finding such an object is positive. And in particular, we maybe want to avoid a bunch of bad things. We want to satisfy certain constraints. And these constraints define something that we don't want to happen. And these are the bad events, say E1 up to EM or something. And if they are all independent, then of course, there is some chance that you find something that avoids all of them. But the local lemma is saying is even if they are kind of somewhat dependent, as long as the dependency is small relative to the kind of probability of these events, then we can still find such a object that avoids all the bad things. And here the parameter P will be the upper bound on the probability of the bad events, and the delta would be the number of events that any other event can depend on. And the condition, of course, is something like E times P times delta less than or equal to 1. And if that's true, then we know that there is a positive probability, typically exponentially small, but still positive probability that we can avoid all the bad events. And today I'm going to talk about some algorithmic questions. And the sort of typical application of the local lemma in computer science is the satisfiability problem. And that's what I'm going to define next. It's a kind of a classic problem, arguably one of the most important ones in computer science. You are given a Cnf formula. So it's a big N of a bunch of clauses, and each clause is all of several literals. And the literal is just a positive or negative appearance of a variable. And the question is whether this is satisfiable. So for this to be satisfiable, you must find an assignment of all the variables so that every clause is satisfied, and each clause is satisfied as long as one of its literal is true. Okay. And so we will use this key set to denote the case where every clause has exactly k literals. So the example I'm giving here is not really kind of a k set for any k because it has varying size of the clauses, but fixing the size will make things easier later on. Also, we sort of assume there's no kind of repeated appearances of variables. And this is the sort of the first NP-hard, NP-complete problem introduced by Cook and Levin in the 70s, and it's NP-hard even if k equals 3. And this sort of originates like this whole NP-hardness theory, and it's also kind of an important problem in practice. And to see why this kind of fits in the local lemma setting is quite simple, that the thing we want to find is a satisfying assignment. The bad things we want to avoid are these kind of all false assignment for each clause. So for example, if the clause is x2 or x3, then the bad thing is x2 equals false, x3 equals false. Okay. And So then dependency is basically how many clauses that share a variable with another clause, right? So let me be more precise. What we are going to really talk about is kind of bounded degree k-set problem. So here is the local lemma once again, and because each clause, I'm assuming it has like exactly k literals with no repeating variables. Then the probability that it is unsatisfied under a uniform distribution is like 2 to the minus k, because each literal has a half probability to be true. For all of them to be false, it's 2 to the minus k. And we're going to assume that each variable appears in at most d clauses. So if you think about kind of incidence graph where you have variables and clauses as the two partitions, this is a bipartite graph, and the variables in a clause, sorry, a variable is connected to a clause if it is in the clause, then this d would be the degree of the variable side. Okay, so that's why I call it bounded degree k-set. And in this setting, the dependence parameter delta is basically the number of clauses that share variable with another clause. So that's something like k times d. It's more like k times d minus 1, but it doesn't really matter. It's a small difference. And then the Lovász local lemma condition, EP delta less than or equal to 1, will translate to something like k is larger than log d plus some lower order terms. All right, so this will be the condition that we are interested in, the type of condition we are interested in. And the local lemma tells us there exists a satisfying assignment as long as this is satisfied. This is quite good because d would be, we can allow d to be exponentially large in terms of k. So that's a kind of a not too stringent constraint. Local lemmas tell us there exists a satisfying assignment, but being kind of a more computer scientists, like we want to find a satisfying assignment. We are not satisfied with there exists something. And so there has been many kind of algorithmic work towards this goal, and perhaps one of the most famous and important one is the algorithm by Moser and Tardos, that they gave a polynomial time algorithm to find such a object that satisfies the local lemma condition. In particular, if we focus on this k-set problem, then basically it says under the same kind of assumption on the parameters, we can find a satisfying assignment in polynomial time. And in fact, it's more like in linear time. It's a really fast algorithm. And this is a very beautiful result, not only in its kind of analysis, but also in the algorithm itself, because the algorithm is extremely elegant. It's just give each variable a uniform random value, or maybe according to the probability distribution you are given at, randomly assign each variable, and then some clauses will be violated, and therefore you pick a arbitrary violating clause, resample all the variable inside it. Keep doing this until all clauses are satisfied. And what they showed is that this will under the local lemma conditions, this will terminate very, very fast in like roughly linear time. Okay, so this is basically kind of solve this problem of finding an algorithm under the local lemma condition. Okay, and as my title kind of hints, what I'm interested in is sort of a sampling question. Instead of, I'm being quite greedy here, right? Instead of finding one solution, I want to generate a kind of an arbitrary solution uniformly at random. And why is this useful? Why do I interested in this? Sampling can allow me to do a bunch of things. For example, I can approximately count the number of solutions. To exactly count the number of solutions would be a computationally hard problem. We are not expected to do that in polynomial time, but approximately counting can be done. Also, I can use this to say estimate the marginal probability of variables. I can estimate the average number of variables that are true in satisfying assignments, etc., etc. I can do a bunch of things. And also sampling is useful in other settings, like in software testing. Usually they want to generate a random instance that satisfies some constraints. So that's also this kind of sample something that satisfies constraints situation. But the bad news is that sampling, it turns out sampling is harder than finding a solution. So sampling can be hard, even if the problem of searching for a solution is easy in the sense that it's doable in polynomial time. And in particular, even under the Lovász local lemma condition, sampling can be NP hard. And what I mean by that is in the next slide. So a few years ago with Ivona, Andreas, Leslie, and Daniel, we showed that if k is, say, less than 2 times log d, or in other words, d is like 2 to the half k, so here all the log are base 2. Okay, so if k is less than 2 times log d, then sampling satisfying assignment is NP hard. And this is even restricted to no negation case. So basically the so-called monotone case. You may imagine that the set is difficult because you may have kind of positive and negative appearance of variables. And if there's no negation, the finding a satisfying assignment is easy, right? You just set everything to be true. But it turns out that even in that case, even under this k less than 2 times log d condition, the sampling problem can be NP hard. And this is in contrast to the algorithmic result by Moser and Tardos that if k is larger than log d, then we can find a satisfying assignment. So there's overlap in the hardness result and this in the sampling hardness result and the searching easiness result, right? So there is a regime where k is like between log d and 2 log d that the find the solution is easy, but if you want to sample one, it becomes NP hard. Okay, so this is kind of a naturally stimulate a question that can we really do sampling sort of beyond this threshold? Like, is this the correct threshold? Like whether the algorithm, whether efficient algorithm exists. Okay, so I'm interested in this open problem that is there an efficient algorithm to sample satisfying assignment given k larger than, roughly larger than 2 log d. And there have been a lot of progress on this problem. So here are a few. So one of the results that kind of directly complements the hardness results is due to Herman, Sly, and Zhang. They showed that this straightforward global dynamics, which is a Markov chain approach, similar to what I'm going to talk about today, they show that it has mixing time n log n. So that means you have a polynomial time algorithm to approximately sample from the desired distribution. And their condition is that k is larger than 2 log d, which is great, exactly what we want. And they have this assumption that is the monotone case, there's no negation. So this is directly complementing the hardness result we have. However, having this assumption on no negation, this makes the hardness results harder, but it makes the algorithms easier. This does not imply algorithm for the general case. In another kind of a joint work with Mark Jerome and Jingcheng Liu, we kind of come up with an alternative algorithm to Markov chains, which we call partial rejection sampling. This is more of an adaptation of the Moser-Tardos algorithm to the sampling setting. And we show that this partial rejection sampling algorithm terminates in linear time if k is larger than 2 log d, and also if there's no small intersection among the clauses. So here, what we are assuming is that 2 clauses are either have no intersection at all, they don't share any variable, or they share many variables. In the in kind of the k equals 2 log d situation, our assumption would be 2 clauses will share half k variables, right? They must either they don't share anything at all, or they share many variables. So this is quite artificial, right? But what's the reason we do this is we analyze this case is that this is exactly what happens in the NP hardness result. So this is kind of complementing the NP hardness result in another direction. But either of the two I talked about have these structural assumptions. What's kind of the breakthrough is due to Moitra, that he showed that linear programming based algorithm, which means it can be deterministic for approximate counting. If k is like 60 times log d, so it has this very big constant, but he has no other assumption on the structure. But kind of a slight downside of his algorithm is that his algorithm has running time n to the k squared d squared. So if k and d are fixed constants, then great, this is a polynomial time algorithm. But if k and d grows with n, this is no longer polynomial time. And also, you know, this is a very high exponent. So that's not what we want. Excuse me. And what I'm going to talk about today is a Markov chain-based algorithm, which is different from the linear programming algorithm, but we're heavily inspired by monetized result, of course. What we did is that we improved the constant to 20, so it's okay. So some improvement is not too important. What's really motivate our work is that we improved the running time from n to the k squared d squared to near linear time for fixed k and d. And sort of in general, it's still like polynomial time whenever k and d, I mean, whatever k and d are. Yeah, so here this delta is like a small constant. It's a part of our constraint, but typically it is very small. So it's the main part is like n to 1 plus delta, which is almost a linear time result. Right, and this is basically where it's at, like last June. But a year later, there have been lots of exciting progress, and in particular, a result by Jane, Pham, and Wong, which I probably pronounced terribly wrongly. They improved the condition, this k larger than 20 log d to something like 5.7 log d. Okay, so the constant has been greatly improved. And basically, they are doing the same algorithm, but they have some improved analysis. They more or less kind of incorporated the analysis from Herman, Sly, and Zhang into this into our algorithm. But the algorithmic ideas are roughly the same. It's just the analysis becomes better. So I will more focusing on the algorithmic ideas. All right. So these are the results. And maybe before going to the result, any questions? Before going to the algorithm. Okay. Let me try to talk about our algorithm, and it's kind of is doing what this picture is hinting at. Okay. And so. All right, so if you want to sample from a distribution, here is a uniform distribution over sci-fi assignments. The standard off-the-shelf algorithm to do is global dynamics, which I mentioned earlier. Sometimes it's also called Gibbs sampling. So what it does is the following. So here is a kind of a example of the CNF formula. This is like 3 CNF formula. Every clause has 3 literals. I'm drawing this incidence graph where it's bipedal graph. One side is the variables, the other side are the clauses. And each variable is connected to a clause if it is in the clause. And if it's like a negative appearance, if it's a negation, then I draw it in red. So here in this example, what you are going to do for the global dynamics is basically you give some initial value. And in this particular case, I can assign everything to be true to satisfy all the clauses. And then the global dynamics or Gibbs sampling will do is to randomly choose a variable and try to resample its values. And here by resampling, I'm conditioning on all the rest. So maybe I randomly choose an x2. Okay, it's not really random. I designed it, but let's say I chose x2, and now I want to resample its values. And my constraint is that I want to satisfy all the clauses still. And in this particular case, it can be checked that x2 is in like clause C1, C2, and all of these two, both clauses are satisfied with other variables other than x2. Therefore, x2 can be either true or false. And therefore, okay, I can give it an arbitrary value, true or false. So it will be a coin flip, right? It will be either value with half probability, and maybe I assign to false. Okay, great. This is one step of the collaborative dynamics. And basically, you want to keep doing this until it's kind of mixed. But the problem is that, let's say in the next step, I've chose x1. Here, the trouble becomes that I cannot flip x1's value because x1 is in clause C1, C3, and C3 has other two variables x3, x7, but both of them are true, but the appearances are negated. Therefore, C3 is not satisfied unless x1 is true. In some sense, I'm forcing x1 to be true, and therefore, in this step, I have only one choice. I don't have two choices anymore. I have to assign it to be true. And this will become a big problem for Markov chains because that it's kind of conceivable that you will be trapped in some areas where any of these local flips cannot be done. All the variables are kind of frozen. You cannot move anywhere outside that sort of a local region, and this indeed is the case. So before giving such an example, maybe let me briefly talk about what we want about Markov chains, right? And here I have some cartoon, right? And the kind of square is the space of all assignment. So in the setting of a k-set, it is the space of all Boolean assignment 0, 1 to the n. So it's like Boolean cube. And the green area is the solution space, or the satisfying assignments, which I really want. And what I like is the first scenario, right? I have a very well connected green area. In each step of the Markov chain, I do some random local moves, and I start from, let's say, the black point, and I can go to anywhere very quickly. And therefore, if I start from the black point, I do this random walk in a very short amount of time, I will be uniformly at random over the whole green area. Here, these spaces are kind of exponentially large. Therefore, I need to be kind of a so-called mixing in time logarithmic with respect to a state space. So I have to be very well connected. And so the first scenario is fast mixing, great. But however, in some other situations, you will have this kind of bottleneck. This whole region is not very well connected. You will be trapped in one side of the whole solution space for a very, very, very long time, typically proportional to the size of the whole green area, whole solution space, which will be exponentially large. It will be trapped there for a long time until you go to the other side. So in order to get an almost uniform distribution over the whole solution space, it will take exponential amount of time. That's slow mixing. That's bad. But what is worse is that in the third picture, I have these spaces that are not even connected, right? I may not go anywhere, and this is exactly what happens for k-set. Okay, I have these trapped regions, areas where no matter how I do these local flips, I'm not going anywhere. I cannot get out of these smaller green blobs, but I want a uniform distribution over all of them. Okay, that's really kind of difficult to do, and not just difficult. That's like impossible, right? If you do only local flips. So all right, so that's a problem, and to see it more, to say it more precisely, here's kind of an example. So again, I have these formula. I have a bunch of clauses. Each clause is all of k literals. Therefore, it kind of disallows one particular assignment on that k variables. For example, if my clause is like x1 or x2, etc., all positive, then we cannot allow all of them to be false. So each clause kind of forbids one particular assignment on k variables. And therefore, what we can construct is that we can kind of eliminate, we can forbid assignment of a particular Hamming weight. So say I forbid all assignment of Hamming weight I using these clauses, then if I start from say Hamming weight 0, then I cannot do local flips, go to say Hamming weight n or something, right? Because I will eventually, each step of the Markov chain will change the Hamming weight by 1. And if I go by one, etc., eventually I want to go to n, but that means I will have to go through these forbidden areas. So we cannot, so if we do that, then we cannot have a connected solution space. And that's very easy to do. The reason being, I can simply say, for example, I want to remove all the Hamming weight 1 assignment. I can simply have these clauses. C1 forbids x1 to be true and x2, etc., to be false. C2 forbids like x1 to be true, x2 to be, sorry, x1 to be false, x2 to be true, everything else to be false, etc., etc. I can have only like k clauses to forbid Hamming weight 1 assignment, and in general, I only need something like k choose I to forbid Hamming weight I. And when I is like small, this is much smaller than say 2 to the k or 2 to the half k, which is the degree of the variable. So I'm still within the parameter regimes on the sort of assumption of the degrees of the variables. Like here, these k clauses, each variable here is like degree k. So the degree is well within the threshold, but yet the solution space is disconnected. So that's bad. That's something we want to overcome. And indeed, it has a very simple solution, actually. Otherwise, I won't be here to tell you about it. And this is what I hinted at the kind of the section head at the picture. So basically, what we are dealing with is a kind of a high-dimensional space where I'm having some disconnected components all over the space. They are not connected, which is bad. But if we project them down to a smaller dimension space, if they could be connected. Like here is some picture that like the picture above is a plane that you have 2 pieces, but on the wall, the shadow is connected. And this is exactly the idea behind our algorithm. Basically, we want to do some kind of projection like this. And then we run the global dynamics on the projected distribution, which is not a uniform distribution over all satisfying assignment anymore. And it's some complicated distribution. We actually don't have a good control of it. We have some control, but not very good control of it. But still, we can run the global dynamics. And this projected distribution is defined by a procedure called marking. We mark certain variables, very carefully chosen, and we kind of focus on only the marked variables, and then we run Markov chains on those variables only. Right, so this is the basic idea. And to be more precise, here is the algorithm. We want to sample from this uniform distribution over all satisfying assignment. The first step we do is to mark a set of variables. I will talk about the marking in the next slide. And then we run global dynamics on the projected distribution. How to run this is actually also non-trivial, which I will talk about later. But we show that under the assumptions of our result, this mixes in n log n time. Therefore, if we run it for n log steps, we get an approximate sample from this distribution. But still, that's only on the marked variable. We still need to sample from the remaining variables. We want a full assignment. So we do rejection sampling on the remaining part, and we can show that rejection sampling will succeed in a very short amount of time. And rejection sampling is basically you uniformly come up with the assignment. If it satisfies everything, great. If it doesn't satisfy something, then you kind of discard it completely, and you generate another sample and check if it is satisfied until you find one. Okay, and finally, of course, we output the combination of these 2 assignments. Okay, and there are several pieces of this algorithm. The first step is the marking. And the marking is kind of a balancing act between 2 things. On the one hand, we want each clause to have some amount of variables marked. And also we want some amount of variables unmarked. And in particular, here we write down a few inequalities and we solve the kind of the best constant. But the constant here are not so important. The important thing is that we want a linear fractions of the variables marked and also a linear fraction of variables unmarked. And the existence of the marking is guaranteed by the local lemma, and we can use the Moser-Tardos algorithm to find such a marking very efficiently in linear time. So this is basically, this processing step is basically for free. Okay, that's something we want to do for the marking. And to be more precise, why do we want to do the marking? And on the one hand, if I have many variables marked, and if I kind of assign uniform values to them, then, oh, well, not uniform, maybe, but something like close to the desired distribution, then in fact, uniform, I think, is also works in our setting. Then with a very high probability, the rest of the kind of instance graph will shatter into connected components once you remove satisfied clauses. Because if a clause, let's say it has k variables and half k of them are given a random value, then you already have a very high probability to satisfy this clause. It won't satisfy all clauses, but what we can show is that the remaining part, it may still have like linear amount of variables, but each connected component will be small. So it will be log n size. So that's something we'll use later. So that's nice. But on the other hand, we cannot afford to mark too many variables. The reason being that we want to, basically still we want to kind of make sure the state space is connected. If we mark too many variables, the state space will become disconnected again. And more importantly, we can apply the local lemma to show something like if there are many variables that are kind of free, they are not fixed, they are not marked, therefore we don't give any assignment to them, then any of the remaining variable will be very close to the uniform distribution. So the marginal probability is very close to 1/2. Notice that here the error is something like exponentially small in k. But this is not good enough to do kind of a straightforward sampling, because if you want to do sampling, what you really want is kind of inverse polynomially small error. And here the error is very, very small, but it's small with respect to k instead of with respect to n. So it's a constant error, albeit very small. So what we do for the marking is to kind of balance these two facts. We don't want too many unmarked, we want many unmarked variables so that the marginal probability of other variables are close to uniform. And also we want many marked variables so that the remaining connected components have small size. Okay. So the main sort of things to show for the algorithm is the following. So first of all, we need the Markov chain to be rapid mixing. Otherwise, what's the point of running that, right? We don't really want to run a slow Markov chain. And the second point is that because now we are running the global dynamics on the marked variables, we need to show that this can be done efficiently, namely in polynomial time. And in fact, this cannot be done exactly efficiently, but we will do some approximation. And this approximation will, again, depend on the rejection sampling. And therefore, so what I'm saying is that in the third step, at the end of the algorithm, we need to reject sampling for the rest of variables. And in fact, in every step of the Markov chain, when we want to sample the marginal distribution of one of the marked variables, we will do the rejection sampling step as well to approximate the marginal probability of that variable. And in our paper, we kind of showed the rapid mixing result using the path coupling method. And this is where the Jane, Pham, and Wong result improved on. So they basically gave something called a information percolation argument to replace the path coupling. And the path coupling is basically kind of tracking how it's a simplified way to kind of tracking how disagreement percolates. And the information percolation is a more sophisticated way to track how disagreement percolates, roughly speaking. And the second and third point, as I said, they are basically done by the same thing. They are done by this rejection sampling step. So they are actually showed together. Okay. So let me give more details about this. So here I have a kind of an instance. Once again, I'm drawing it as a hypergraph. Here each hyperedge has size 4. And I did the marking so that every hyperedge has at least one marked variable. It could have 2, but it has at least one marked variable, and also at least 2 unmarked variables. You could have 3 unmarked, but it have at least 2. So what we want to do is that basically, basically we have these marked variables that are kind of fixed, and we want to know the marginal probability of the top variable. This problem of kind of computing the marginal probability is actually number be hard, which means that we cannot expect to do that in polynomial time. But we can do this rejection sampling because we know that once the other 3 variables have their values, so that the remaining graph will shatter into small connected components. And therefore, each component have like size log n, and therefore we can do rejection sampling to find the marginal probability. Well, not just the marginal probability, we actually gave a sample according to the marginal probability. That's exactly what we do. And once we have that, we kind of erase all the unmarked variables values. We don't want them to be assigned, so we kind of forget about them. We do some. In fact, this is like a projection step. We erase them, and we continue. And what we show is that this rejection sampling will terminate in like n to the delta steps. Delta is the small constant I talked about earlier. This will terminate with high probability. We cannot do this exactly, but with a very high probability, we will succeed. Okay, so this is basically how we implement the global dynamics. And the overview of our proof is something like this. We start with the marking. On the one hand, we guarantee that each clause has many marked variables, which implies that the remaining part are small disconnected components. And then we do rejection sampling on them. We get this efficient implementation into the delta time implementation. And on the other hand, we have guaranteed that each clause has many unmarked variable, which implies that every other variable are kind of uniform, almost uniform locally. And this error is so small that we can pull off a path coupling argument. And in the traditional kind of standard path coupling argument, when you have a disagreement on some variable, what you want to do is that you want to show its influence on the neighboring variables are small. But here, because we have many variables that are kind of free, we're not giving any values to them. So once you have a disagreement, it will affect through these unmarked variables to every other marked variable. So its influence will not be constrained to this small local area. It will be over the whole thing. And so this is basically the main difference from kind of standard path coupling in our argument. But you can imagine that this influence, although it goes to everywhere, this influence will decay as long as you go, right? If the variable is further away from the variable you are disagreeing on, this influence will decay very rapidly. This is due to this local uniformity kind of properties. And basically, the information percolation argument is a more careful way to do this argument, do this analysis. This leads to a n log n mixing time. And overall, we have this n to the 1 plus delta kind of running time. Okay, so that's the overview of our whole proof. And before kind of wrapping up, I will kind of give some intuition about the rejection sampling step. So you may wonder, like, because we know the connected component have size log n, like, why don't we just do a brute force enumeration, because 2 to the log n is still n, is like polynomial time. The reason is that to be more precise, we can show that the size is at least d times k times log n. I think the truth is probably some polynomial in d and k, but it's very easy to show it's at least d times k times log n. And therefore, if you do a brute force enumeration, it will take time n to the d times k, which again is more similar to the Moser algorithm, which is something we want to avoid, exactly the thing we want to avoid. So that's why we do the local lemma. And the interesting thing is that the local lemma not only shows that the probability of uniform assignment satisfy everything to be positive, local lemma actually gives some exponentially small lower bound. However, here our size is log n, so this exponentially small lower bound is still like polynomial, which is n to the minus delta, if you work out the calculation. And amazingly, it doesn't depend on d and k. So somehow, if you do rejection sampling, the success probability is an inverse polynomial. Therefore, in like n to the delta steps, we maybe multiplied by some log n, you will succeed with high probability. So that's basically why we choose to use rejection sampling instead of brute force enumeration. And right, so that's basically everything I want to talk about the algorithm and the kind of the techniques. Okay, so any questions? Okay, so I can continue. I'm gonna wrap up. Let me first mention some other kind of related recent work. With Andreas, Leslie, and Quan, we give an algorithm that approximately counts the number of satisfying assignment of a random k-CNF formula. We can also do like sampling, approximate counting, and sampling are kind of quite related. Our assumption is that the density of the random formula, which is the number of clauses divided by the number of variables, is something like 2 to the k over 300. So 300 is a very bad constant. Of course, it's roughly corresponds to the 20 in our result, or the 5.7 in the more improved result. In this scenario, we get 300, apparently bad. But on the other hand, this improves the previous best result, which works for 2 to the log k over k, which kind of goes to 0 as k gets large. In contrast, we get 2 to the k over 300, which is exponentially large in k. So this is actually, in terms of like asymptotic order, this is a big improvement. Although our density, our constant is terrible. And the algorithm is based on the linear programming approach by Moser. But the main thing here is that for a random instance, you will, with high probability, we will get some high degree variables, something like log n over log n. So the main thing we need to deal with is how to handle those. But still, the running time here is similar to Moser's, like n to some big exponent, and here the exponent is actually exponential in k, which is apparently very bad. But for fixed k, this is polynomial time. And so there's a natural question that can we apply the Markov chain approach to the random formula setting? And I believe that can be done. And in fact, we have some ongoing work, and more or less everything I talked about today will break. You need to replace each ingredient with some other arguments, but I think it can be done. Okay, so this is for the random instance case. And as I mentioned earlier, there have been a lot of progress since our paper in this past year. In terms of the algorithm itself, the conditions has been improved to 13 first by 2 of my co-authors, Feng and Yin, together with Kun He. And then they basically did a more careful path coupling analysis. And then later, Jane, Pham, and Wong, they kind of did a sophisticated information population analysis to improve the constant to 5.7. And but kind of the main focus in this work are to generalize our result to a more general setting, local lemma variable, local lemma setting, in our paper, in the paper I'm talking about today, we focused on the Boolean case. So basically, each variable has only 2 possible values. In general, you may have, like for example, you may want to look at hypergraph coloring. Then each variable may have a Q colors, where Q is like a parameter. It will show up in the local lemma condition. And some of the ideas here will not work, but the rough idea of Markov chain plus projection still works. But you need to do this more cleverly. You need to kind of do something with the Q, with the size of the domain for each variable. And so Feng, He, and Yin first generalized this to this a more general setting, and their condition is still like p times delta to the 13th. So in the local lemma, you have p times delta roughly constant, and our hardness result is like p times delta squared being constant will make things hard. So we need to assume some exponent larger than 2. Here they get 13, and this was improved by Jane Pham and Wong to 3.04 something. And in another kind of direction, Jane Pham and Wong, they improved the Monetized linear programming algorithm, which also is specialized to sort of the Boolean case. They also improved that to the general case with a much better condition, p times delta less than equal to 1, roughly. And their main improvement is some kind of a new coupling trigger, although I didn't talk about the coupling too much. But kind of this is sort of a new idea in that paper. So basically, for this deterministic but slow algorithm, we have p times delta less than roughly constant condition. And for the fast Markov chain algorithm, we have p delta to the 7.04 kind of condition. Right, go to the last page. So when I first gave this talk, my first open question is, can we do this for other kind of local lemma settings like hypergraph coloring? Now this has been answered by Feng, He, and Yin, and together also with also by Jane Pham and Wong. Another natural question is, can we get a more efficient algorithm towards this conjecture, the threshold? Now our best algorithm is like 5.7, which is very close to 2, but it's not 2 yet, right? And it seems our current method has been pushed to the limit. We may need some new algorithm to really approach this threshold. And maybe we need to get rid of the marking in the Markov chain-based algorithms, or maybe we need to do some more clever counting in the analysis. In these analyses, we're typically counting paths or 2-3 trees, etc. But in the Moser and Tardos algorithm, they count the number of so-called witness trees, which is a more efficient way to do this counting. So can we incorporate that kind of analysis? And lastly, there's this question of, can we apply this projection idea to other scenarios where maybe you have something slow mixing, but after the projection, it is fast mixing, but also you can efficiently implement this projection and the global dynamics. I don't know this yet. This remains like the only application I know of the projection idea, but there may be others. This sounds like a very general idea. Yeah, so that's everything I want to say, and thank you for your attention.
Great, thank you very much. I think we have just a couple of minutes for a quick question if anybody has something to ask. No one else wants to jump in, I can perhaps ask something I was wondering about. I think you maybe partially answered this when you talked about the random formulas. Is there an obvious reason that none of these ideas can work if you don't have something that is guaranteed to be satisfiable to start with?
Yes, of course. Like in the basically we are operating under local lemma condition with guarantees something must be satisfied. If you don't have some, sorry, if you have formula that doesn't have a satisfied assignment, the local lemma kind of condition will break. And in fact, we need to assume something much stronger than local lemma itself, which means we need not only one satisfied assignment, we need the satisfied assignment to be kind of sufficiently many, and they must satisfy some good properties. due to our condition. So yes, so the kind of in the random setting, the threshold for satisfiable is something like 2 to the k, I think. Can't remember it off my head, but I think it's something like 2 to the k. But here that our density is much smaller, 2 to the k over 300, and that don't believe it goes all the way up to 2 to the k. Yeah.
Great. I think we're probably pretty much out of time. So thank you again. Let's do another round of applause.